In section 6.5, we are factoring binomials, and our objectives are to factor the difference of two squares, which is in the form of a squared minus b squared, and the factors are a plus b and a minus b. The second objective is to factor the sum or difference of two cubes. The sum of two cubes is in the form of a to the third plus b to the third, and this could be factored into one factor as a plus b, and the other factor is a squared minus ab plus b squared. And the difference of two cubes is in the form of a to the third minus b to the third, and the factors are a minus b as the first factor, and the second factor is a squared plus ab plus b squared. So in this lecture, we're going to be identifying polynomials that follow either the difference of two squares or the sum or difference of two cubes. To factor polynomials that are in the form of a difference of squares, where the model equation looks like a squared minus b squared, the factors are a minus b and a plus b. And the reason this works out is you can check this using the FOIL process, where the first a times a is a squared, the outer a times a plus b is a positive ab, the inner is this minus b times a, or minus ab, and the last is negative b times a positive b, which is a negative b squared. The middle two terms are opposites, so the polynomial can be reduced to a squared minus b squared. So we're looking out for polynomials that are in the form of a perfect square minus perfect square, and then finding the two binomial factors. Since our first equation, x squared minus 9, can be written as a difference of two squares, where x is squared gives you x squared, and 3 squared gives you 9. So this is in the form of a squared minus b squared. So the two factors are going to be x minus 3 and x plus 3. That is our polynomial in factored form. We use the difference of two squares. You can always check your work by doing FOIL, where we multiply the first times the outer times the plus the inner plus the last. So we have x squared plus 3x minus 9, and that middle term simplifies so that we get x squared minus 9. In example B, we have x squared minus 25. This also follows that model equation of a perfect square minus a perfect square, where x raised to the second power is x squared, and 5 raised to the second power is 25. So in this case, our factors can be written as x minus 5 and x plus 5. We can check our final answer using first, outer, inner, last. The first is x squared, the outer is plus 5x, the inner is minus 5x, and the last is minus 25. Simplified, we get x squared minus 25. Example C, we have y squared minus 24. So y is our first term that's squared, that's a perfect square, and 64 is the same thing as 8 to the second power. So this is a perfect square minus a perfect square. Our factors can be written as y minus 8 and y plus 8. We can check our answer using the FOIL step, where it's the first y squared plus outer, inner, and last plus 8y minus 8y minus 64, and simplify, we get y squared minus 64. Example D, we have 4a squared minus 9. This also is in the form of a difference of two squares. 4a squared can be written as the quantity 2a to the second power, and 9 can be written as 3 to the second power. So using that model equation with 2a and 3, our factors are 2a minus 3 and 2a plus 3. We can check our final answer using first, outer, inner, last to get 4a squared plus 6a minus 6a and minus 9, where the middle term are opposites, so we simplify the polynomial as 4a squared minus 9. Example E, we have 49x squared minus 1. This is also a difference of two squares. 49x squared can be written as the quantity 7x to the second power, and 1 can be written as 1 to the second power. So our factors are 7x minus 1 and 7x plus 1. We check our answer using the FOIL process. First, outer, inner, last gives us 49x squared plus 7x minus 1, simplified to get 49x squared minus 1. In example F, we have 9a squared plus 16b squared. Now, although both of these are perfect squares, in fact, we can write them as 3a quantity squared plus 4b quantity squared. This actually cannot be factored. There is no special formula for the sum of factoring the sum of two squares. The formula we are using is for the difference of two squares, not for the sum. So we can say that this cannot be factored. We can also say that this polynomial is prime. Example G, we have 36m squared minus 100n squared. This can be factored as well. We recognize that this is a difference of two perfect squares. 36m squared can be written as 6m to the second power, and 100n squared can be written as 10n quantity to the second power. So our factors will be 6m minus 10n and 6m plus 10n. We can check our answer using FOIL, first, outer, inner, last, and we get 36m squared plus 60mn minus 60mn minus 100n squared. Simplified, we get 36m squared minus 100n squared, and that's the same thing as what we started off with, so we know that our factored form is correct. In example H, we also recognize that this is a difference of two squares. 1/4 x squared can be written as 1/2 the quantity of 1/2 x squared minus 1 squared. So our factored form can be written as 1/2 x plus 1 and 1/2 x minus 1. And again, when you're writing factors, it doesn't matter what order they appear in, because when you multiply, it all simplifies in the end. And then we can do our check step here by using the first, outer, inner, last. We get 1/4 x squared minus 1/2 x plus 1/2 x minus 1, which simplifies to 1/4 x squared minus 1. Example I, we have 64 minus 9 over 25a squared. This is also in the form of the difference of two squares. 64 is a perfect square. We can write it as 8 to the second power. And 9 over 25a squared is also a perfect square that we can write as a quantity 3a over 5 squared. So the factors will be 8 minus 3a over 5 and 8 plus 3a over 5. We can check our answer that those indeed are the two factors by using the FOIL process, first, outer, inner, last. We get 64 plus 24a over 5 minus 24a over 5 minus 9a squared over 25. Simplified, we get 64 minus 9a squared over 25. That's what we started off with. So we know our polynomial is in the correct factored form. Now we're moving on to polynomials that are either a sum of cubes or difference of cubes. And the model equation for the sum of cubes is in the form of a cubed plus b cubed, and the factors are a plus b and the factor a squared minus ab plus b squared. For the difference of cubes, the polynomial is in the form of a to the third minus b to the third, and the factors are a minus b, and the second factor is a squared plus ab plus b squared. We can recognize that these are in the form of the first example, 8x to the third plus 1 is in the form of a sum of cubes. Since 8x to the third can be written as the quantity 2x to the third, and 1 is 1 to the third. So our a is going to be the 2x and the b is equal to 1 using the model equation that we have here. One factor is 2x plus 1, and then we have a squared. So we take the first 2x and square it to get 4x squared. Minus a times b is going to be minus 2x times 1 plus b squared plus 1. So that's our answer in factored form. We use the model equation for factoring the sum of cubes. You can check this by using the distributive property. The FOIL process doesn't work since we have too many terms. So we first begin by distributing the 2x, and then we're going to distribute the 1. In our check step, we get 8x squared minus 8x to the third minus 4x squared plus 2x, and then distributing the 1, we get plus 4x squared minus 2x plus 1. And by combining the like terms, we see that we have a minus 4x squared and a plus 4x squared. Those are opposites. And a plus 2x and a minus 2x are opposites. So this can be written as 8x to the third plus 1. And that's what we started off with. So our correct answer in factored form is given as a binomial factor of 2x plus 1 and the trinomial factor of 4x squared minus 2x plus 1. Example B is a to the third minus 1. This also is in the form of one of those special cases. It's a difference of cubes, and a to the third minus 1 to the third, those are both perfect cubes, so we're going to be using the difference of cubes equation, where the first factor is going to be a minus 1, and the second factor is the first term squared, a squared, plus a times 1 plus b squared. So this is our final answer in factored form by recognizing that this is a difference of cubes. We can use the distributive property to check our work. First distributing the a, we get a to the third plus a squared plus a, and then distributing the minus 1, we get minus a squared minus a and minus 1. By adding those and combining like terms, we get a to the third minus 1, which is what we started off with. So that's the correct factored form for the polynomial. Example C, we have 64x to the third plus 27y to the third. This is in the form of the sum of two cubes, where 64x to the third can be written as 4x to the third power, and 27y cubed can be written as 3y quantity to the third power. So our a is going to be 4x and our b is 3y. Since this is a sum of cubes, we're using the first model equation to find the two factors, the first being a plus b, or 4x plus 3y, and the second being a squared. We've got to take this 4x and square it to get 16x squared, minus a times b, minus 4x times 3y is minus 12xy, and then the last term in the second factor is b squared, so that's going to be, let's see if I can, 9y squared. This is our answer in factored form, and we can check this using the distributive property, first distributing the 4 to get 64x to the third minus 48x squared y plus 36xy squared. When you distribute the 4, you get those three terms. Distributing the plus 3y, 3y times 16x squared is going to be a plus 48x squared y. 3y times the negative 12xy is a minus 36xy squared, and then 3y times 9y squared is 27y to the third. By simplifying this, we get 64x to the third plus 27y to the third. So we know that our answer is in the correct factored form. In example D, we have 54y to the fourth minus 2y. Now this doesn't look like either a difference of cubes or a sum of cubes. So we need to do something first before we try to apply any of those model equations. I notice right away that both of these terms are even and they both have a common y. So we need to first factor out the GCF of 2y. So factoring out a 2y from both of those terms, it's like dividing out a 2y, and that gives us 27y to the third minus 1. And what we have written in here, inside the parentheses, is a difference of 2 cubes. Because 27y to the third can be written as 3y to the third, and 1 can be written as 1 to the third. So this is a difference of 2 cubes, and we can use this formula to find the factors. Keep in mind that we're going to keep that 2y out in front, and then we're going to factor. We have a binomial factor and a trinomial factor. The binomial factor is going to be 3y minus 1, that's a minus b, and then the a squared plus ab plus b squared is going to be 3y, that quantity squared is 9y squared, plus a times b, or 3y times 1, and plus a b squared will be plus 1. So this is our answer in factored form. And you can check your answer by first multiplying the binomial and trinomial factors together, and then multiply the result of that by 2y. So when you multiply 3y minus 1 times a trinomial, you distribute the 3y to get 27y to the third plus 9y squared plus 3y. And then when you distribute the negative 1, you get minus 9y squared minus 3y minus 1. Simplify this, keeping that 2y out in front. We get 27y to the third, and those will simplify 27y to the third minus 1, and then distribute the 2y to get 54y to the fourth minus 2y. Let's look at example E, 125b to the fifth plus b squared. So this is not a sum or difference of two perfect cubes, but we can factor out a GCF. Both terms have a b squared in it, so our GCF is a b squared. When we factor out b squared, we'll have 125b to the third plus 1. And this can be written as a sum of two cubes. So keep that b squared factor out in front, and we know that 125b to the third can be written as 5b to the third power plus 1 to the third power. So my factors will have a b squared, and then using this model equation for the sum of two cubes, we get 5b plus 1, and then the a squared is going to be 5b quantity squared, or 25b squared, minus 5b plus 1. That's our answer in factored form, and you can check by using the distributive property, multiplying the binomial and the trinomial factors together, and then multiplying the result by b squared. So when you multiply, distribute the 5b, that's going to give us 125b to the third minus 25b to the second plus 5b. Distributing the plus 1, we get a plus 25b squared minus 5b plus 1. And by simplifying that, I get b squared. These are opposites. We get 125b to the third plus 1. And then distributing the b squared from out in front, we get 125b to the fifth plus b squared. In example F, we have a to the sixth minus 1. Now this may not at first look like the difference of two cubes, but we can write a to the sixth as a squared to the third power. So a squared to the third power is your a cubed, and then your b cubed, it would be minus 1 cubed. So we can use the first model equation for factoring a difference of two cubes. And my factors are a squared minus 1, and then the other factor is going to be this first term squared, so we get a to the fourth plus a times b, so it's going to be plus a squared, and then plus b squared, so it's going to be plus 1. Now, we could go back and actually factor this even further, because you should recognize this first factor, a squared minus 1, as a difference of two squares. So that we can factor it even further, as a plus 1 is a factor and a minus 1 is a factor, along with the a to the fourth plus a squared plus 1. So that's our answer in factored form. We can check this by using the distributive property. We can, with the first two factors, we can do the first outer inner last to get a squared minus a plus a minus 1 times that same trinomial, and this is going to be a squared minus 1 because the middle terms are opposites, times a to the fourth plus a squared plus 1. Using the distributive property, I'm going to get a to the sixth plus a to the fourth plus a minus a to the fourth, sorry, that should have been a squared, minus a squared minus 1, and then this is going to simplify to a to the sixth minus 1.